After studying this module, you shall be able to know about three-dimensional structures of alicyclic compounds, learn about the concept of conformation, and understand Baeyer strain theory for predicting the stability of ring compounds and its incorrectness. Identify different types of strains in conformations of cycloalkanes. You should be able to draw energy profile diagrams for various conformations of cyclohexane and other cycloalkanes. Preferred configuration of substituted cycloalkanes. Three-dimensional shapes of organic molecules. We live in a three-dimensional world, and the same is true for molecules. Molecules are three-dimensional entities with well-defined shapes and structures. Though most of the time we see their two-dimensional drawings in books, it is always a challenge to visualize their three-dimensional shapes without the help of the models. The study of stereochemistry of organic molecules allow us to visualize and draw these molecules in a better way, and also to analyze and predict their behavior in three-dimensional space. The shapes of organic molecules depends on the type of bonds, whether it is a single bond, double bond or a triple bond. While the single bonds impart flexibility, the double and the triple bonds imparts rigidity in the molecules. The free rotation around carbon-carbon single bond gives rise to conformations that are interconvertible without breaking any bond, and the restricted rotation around a double bond gives rise to configurations or geometrical isomers which are not interconvertible unless a bond is broken. The free rotation around all single bonds within the same molecule can give rise to various different shapes of the molecule. For example, shown in this figure are the several views of the same molecule. This is a structure of a pea moth pheromone used by female moths to attract a male moth. It can be seen that without changing the bonded structure of the molecule, we can get different shapes simply by rotating the single bonds at specific sites within the molecule. You can see this in the figure given. There are certain rotations in the molecule itself which gives you a different shape. Note that the arrangement around the double bond is never disturbed as their rotation is restricted. The different shapes that a molecule can adopt due to rotation about single bonds are called conformations. Since the single bonds can be rotated to any fractional amount of a degree, it gives rise to new conformation minutely different from the other. Conformations are thus infinite in number and hence are called conformers instead of stereoisomers. The term rotational isomers is also often used. The study of molecular conformations and their relative energies is called conformational analysis. Conformational analysis allows us to relate the shapes of molecules with their chemical reactivity and physical properties. Let us find out about the Baeyer strain theory first. This theory was proposed by Adolf von Baeyer in 1885 and popularly known as Baeyer strain theory. It suggested that the angle strain in cycloalkanes increases proportionally as the deviation from the regular tetrahedron geometry increases. Hence, a cyclopentane ring with an internal angle of 108 degrees would be most stable as it has a minimum deviation from a regular tetrahedral angle of 109.5 degrees. And the angle strain would increase on either increasing or decreasing the ring size as shown in the figure. Cyclopropane has an internal angle of 60 degrees which is much away from the regular tetrahedron angle, then 90 degrees for cyclobutane, 108 which is having the minimum deviation from the regular tetrahedral angle, then 120 for cyclohexane, 129 for cycloheptane and 135 for cyclooctane, and so on. The deviation is increasing further. However, it was soon realized that cycloalkanes except cyclopropane are not planar, and the theory was not correct except for very small rings. Cycloalkanes can bend and twist about their carbon-carbon single bonds to acquire stability. In fact, a puckered ring structure of cyclohexane has a zero angle strain. That means it has a bond angle perfectly equal to a tetrahedral angle of 109.5 degrees. One can compare the stabilities of cycloalkanes by using their heats of combustion data, which is given in figure. The molar heats of combustion data of cycloalkanes are given here. The minimum value of heats of combustion suggests maximum stability. According to this data, the cyclopropane has the maximum strain and the least stable, while the cyclohexane has the least strain and is most stable. Now, let us study the conformations of cycloalkanes. The molecules show strain arising out of non-ideal geometry. The internal energy of molecules is dependent on several factors. These factors are stretching and compression of bonds, which is known as the bond strain. The bond angle distortion, that is given by the Baeyer strain theory as the classical strain. The torsional strain, which arises due to the eclipsing of the two bonds, that is called eclipsing strain. And the steric strain, which is also known as van der Waals strain. And the total strain energy of the molecule is a sum of all these four factors. A molecule will adopt the geometry that minimizes the total strain energy. The method of calculation of total strain energy is spoken as molecular mechanics. Let us study these strains one by one. The steric strain. Any type of repulsion between two closely spaced non-bonded atoms or group of atoms is known as steric strain. The repulsions between the electrons of these closely spaced atoms imparts a destabilizing effect and is the major cause of the overall strain in a molecule. It can be classified into various types of strains as described now. Angle strain, first of all. If the angle between a pair of adjacent bonds on a carbon atom is less than the tetrahedral angle, that is less than 109.5 degrees, then there is a destabilizing effect due to the bond pair repulsion. This is known as angle strain. Now, van der Waals strain. This type of strain arises when the electron clouds of a pair of bulky groups are too close to each other. It leads to an increase in energy of the system due to the electrostatic repulsion of the electron clouds as shown in the figure. There is a repulsion of the electron clouds leading to a destabilizing effect. Another strain is known as torsional strain. When a molecule is able to rotate around a sigma bond, the other three bonds on each carbon atom holding the single bond move relative to each other, resulting in different levels of torsional strain. The relative movement of these bonds can be better understood in terms of dihedral angle. Just look at the figure. A dihedral angle theta is the angle between the two intersecting planes formed by the bonds on adjacent carbon atoms. So, we know that torsional strain is same as the eclipsing strain, which is due to the maximum strain is observed when these bonds are closest to each other, that is in an eclipsing position when theta is equal to 0, that is 0 degrees. Hence, this strain is also known as eclipsing strain. With the rotation around the sigma bond, the dihedral angle changes and consequently the repulsion between the bond pair of electrons also changes. The strain is minimum at theta is equals to 60 degrees, and this conformation is called staggered conformation. And that repulsion is between the bond pairs of two intersecting planes. These bonds lie in the two intersecting planes, defining a dihedral angle. Another one is ring strain. Generally, a ring or cyclic structure is less stable than the equivalent acyclic structure, primarily due to the angle and torsional strain. The extra energy is released when the ring is opened, which is known as ring strain. Let us now look at the conformations of specific cycloalkanes and their respective stabilities in detail. Let us start with cyclopropane, which is the smallest of all rings. In cyclopropane, the 3 carbons should lie in a plane, as any 3 points describe a plane. All the carbon-carbon bond lengths in propane are same, which suggests that the all 3 carbon must lie in the corner of an equilateral triangle. In this geometry, the deviation from the regular tetrahedral angle is maximum from a normal tetrahedral angle of 109.5 degrees to 60 degrees. And hence, there is extensive strain in the cyclopropane ring. This is evident from the large heat of combustion value per methyl group. In fact, the C-C bond in cyclopropane are bent in order to form an equilateral triangle. Further strain is imparted by eclipsing interactions, as all the CH bonds in cyclopropane are eclipsed. And C-C bond rotation to relieve this strain is not possible due to the rigidity of the ring. Hence, cyclopropane is considerably strained molecule and is readily undergoes reactions involving ring opening. The figure shows the orbital overlap in cyclohexane, showing the bent bonds and thus showing the strain in the molecule. Thus, there are reactions which are favorable, which actually requires the ring opening. Let us study about cyclobutane. In cyclobutane, the ring adopts a puckered or a wing-shaped conformation. Though the distortion from the planar structure reduces the torsional strain, eclipse bonds move slightly away, it increases the angle strain. The angle decreases as the ring puckers. So, there has to be a balance between the two structures when the ring puckers to about 34 degrees, that is, when one methylene moves 34 degrees up or below the rest of the 3 carbons, forming a plane. The planar form of cyclobutane, where all the bonds are eclipsed, is just 1.4 kilocalories per mole more in energy than the puckered conformation. This figure shows the puckered conformation of cyclobutane, where the 3 atoms of the carbon lie in the same plane and the 4th one is just above that plane. Let us now see the cyclopentane conformations. Unlike what was predicted by Baeyer, cyclopentane is not entirely strain free even though in a planar conformation. The C-C-C bond angles are close to 109.5 degrees. The eclipse bonds in the planar cyclobutane impart considerable torsional strain, forcing it to attain a more stable puckered conformation. The heat of combustion data indicates that the total strain in the ring. On distorting the planarity, the cyclopentane partly relieves the torsional strain, but increases the angle strain, similar to cyclobutane. And the minimum energy conformation is thus adopted by balancing the two opposing effects. These are 2 conformations which are shown in the figure, which are of comparable energy. One is the open envelope with 4 carbon atoms in the plane and one above or below it. And the other one is twist form, where 3 carbon atoms in a plane and 2 are above or below it. The atoms in the ring rapidly take turns not to be in the plane. That means, it is not that only one carbon atom forms out of plane, but it is by rotation every carbon atom goes out of plane and the 4 of them remains in the same plane. The cyclopentanes have much less well defined conformational properties than cyclohexanes. Shown in the figure is the open envelope conformation of cyclopentane. So, you can see it resembles a kind of a envelope where you have 4 carbon atoms forming the rectangular part of the envelope, and the 5th carbon, which is above or below the plane, forms the envelope jacket. Let us see now the conformations of cyclohexane. As predicted by the heats of combustion, cyclohexane is a strain free ring. It has neither angle strain nor a torsional strain in its chair conformation, and this is because it can pucker in such a way that all of the bonds are perfectly staggered, and in this conformation all of the bonds are 109.5 degrees angle, which is a perfect tetrahedral angle. In the chair conformation, the 4 carbons lie in a plane while 2 lie above and below this plane. You can see in this figure a chair conformation resembles a simple chair which has a seat which is formed by the 4 carbon atoms and a back which is defined by 1 carbon atom going up and the legs of the chair which is defined by 1 carbon atom going below this plane. The 2 types of CH bonds in cyclohexane, and these 2 types bonds are vertical bonds which are parallel to the axis called axial bonds, and the near horizontal bonds radiating away from the equator are called equatorial bonds, and they are slanting up or slanting down as shown in the figure alternatively. You can see that the one which is absolutely lying vertically, either one is up, the alternating bond is down, alternating bond is up, alternating bond is down, these are all the axial bonds, whereas the one showing either slightly up or slightly down position are the equatorial bonds, and that too are alternating, either one is up, the other one is down, the other one is up, the next is down, and so on. So, all 6 axial CH bonds are anti to each other and skew or gauche to equatorial CH bonds, and also to the ring skeletal bonds as shown in the figure, which is showing you the Newman projection of chair conformation of cyclohexane. It is very much clear in the Newman projection how these axial and equatorial bonds are actually lying in an alternative fashion above or down. Note that any pair of axial and equatorial bonds on adjacent carbon atoms are cis to each other, that is, they point in the same direction, either up or down, and any pair of axial or equatorial bonds on the adjacent carbon atoms are trans to each other or anti to each other. Cyclohexane theoretically can exist in 2 different chair conformations as shown in the figure, and the 2 forms can interconvert easily through ring flipping. This is shown in the figure, which is showing that the one carbon atom which was earlier down has been flipped up, and the one which is up was flipped down to give you another inverted chair conformation. The ring flipping is nothing but a rotation of a single bond in the molecule. An interesting point to note in this interconversion is that all the axial bonds in ring 1 becomes equatorial bonds in the inverted chair, that is ring 2, and vice versa. There are infinite conformations of cyclohexane of varying energies besides these chair conformations, and this is due to the rotation around carbon-carbon single bonds within this cyclohexane moiety. Figure giving the energy diagrams of various conformations of cyclohexane. The one which is in the middle is the boat conformation. The other 2 are twist boat conformations, which are shown as the smaller dip in the graph, and half chair conformations, which are shown as the maxima on the graph. These ones are representing the peaks. The ones with the twist boat conformations represents the valleys in the energy diagrams of cyclohexane, which is shown in this figure. We can see that the chair conformation has the minimum energy of all and is therefore called the ground state conformation of cyclohexane. The boat conformation is 6.9 kilocalories per mole higher in energy than the chair conformation. This may largely be attributed to torsional strain among the 4 pairs of hydrogens which is there in boat conformation, and also to some extent to flagpole interactions. The flagpole interactions are shown in the figure, wherein the 2 hydrogens are actually merging into each other, giving rise to some kind of steric strain. So, the major reason for destabilizing of boat conformation is mainly due to the torsional strain, that is eclipsing interactions, and also of the flagpole interactions. In twist boat conformation, the planarity of the 4 carbon atoms is distorted or twisted, and hence the name twist boat. By twisting the planar carbons, the strain due to eclipse bonds in boat is somewhat relieved, and that is why you can see in the energy diagram the twist boat conformation has a lower energy than the boat conformation. The twist boat conformation is only 0.4 kilocalories per mole more stable than the boat conformation. It lies on the lower valleys in the energy diagram. Likewise, the 2 half chair conformations represented by the highest energy peaks are transition states in the interconversion of one chair into another chair, that is the inverted chair. The table summarizes the amount and the types of strain in various conformations of cyclohexane. Let us just summarize these strains. You can see in this table, the chair conformation has no angle strain, it has no torsional strain because all the bonds are in the staggered conformation, it does not have any van der Waals strain, and it has no flagpole strain because no two carbon atoms, hydrogens, are actually bumping into each other in chair conformation. Now, look at the boat conformation. There is no angle strain, absolutely free of angle strain. That means the angle in both conformations are also nearly equal to tetrahedral angle, but there is lot of torsional strain in both conformation, and this is arising out of the eclipsing interactions. There is van der Waals strain and also the flagpole strain in both conformation. Now, compare it with twist boat conformation. Twist boat conformation is slightly different than the boat conformation in a way that it has a very slight angle strain, it has a very slight torsional strain, it has a slight van der Waals strain, but no flagpole strain interactions. Whereas in half chair, the destabilizing effects are much more pronounced as compared to all other conformations. It has large amount of angle strain because of the planarity of 5 carbon atoms. The torsional strain is high, van der Waals strain is also there. However, flagpole strain is not there in half chair conformation, but it is making it the most unstable conformation in case of cyclohexane, and thus it actually exists as a transition state for converting one chair into another chair. These relative energies of conformations are only for unsubstituted cyclohexanes. The presence of substituents can actually change their relative energies, and we will study this a little ahead. Let us see how the presence of one or two substituents on the cyclohexane ring affect the energies of various conformations. Let us start with the single substituent on cyclohexane ring, that is monosubstituted cyclohexane. Let us take an example of methyl substituted cyclohexane. Now, in this case, though all the 6 carbon atoms in cyclohexane are equivalent, there are 2 types of bonds on each carbon. We have just done that. They are named as axial and equatorial bonds. Now, where the substituent can be placed? You can either place it on the axial bond or you can place it on an equatorial bond. Let us take methyl group as a substituent for conformational analysis of monosubstituted cyclohexane. The 2 possibilities we have are either the methyl group occupies axial position or it occupies equatorial position. The 2 can interchange through ring flipping, as we have seen that interchange or ring flipping actually converts all the equatorial bonds into axial and vice versa. Which of the 2 is more stable, methyl group at axial position or methyl group at equatorial position? Look at the figure. If we draw a Newman projection for methyl cyclohexane, we will see that axial methyl cyclohexane experiences gauche interactions between the methyl group and the ring methylene. So, we can see these interactions are known as 1,3 diaxial interactions. So, or a kind of gauche interactions is between the methyl group and the ring methyl carbon, and 1,3 diaxial strain is between the methyl group and the hydrogens on the 3rd carbon atom, or one, just when you skip one carbon atom and goes on to the other carbon atom, this 1 and 3 carbon atom substituents having 1,3 diaxial interactions. Because there is only one hydrogen here, these 1,3 diaxial interactions are not very well pronounced. However, the gauche interactions, which is between this substituent and the methylene group of the ring, is quite pronounced, which destabilizes this. Whereas in equatorial position, no such gauche interactions are there. So, you can see this in the Newman projection in the figure. We will see that axial methyl cyclohexane experiences gauche interactions between the methyl group and the ring methylene, while equatorial methyl cyclohexane has no such interactions, and hence has somewhat lesser energy than the axial methyl cyclohexane. Besides gauche interactions, the axial methyl group experience steric repulsions from the nearby axial hydrogens, which further increases the energy of axial methyl cyclohexane. These steric interactions between the substituent in axial position in C1, that means at C1 carbon atom, and the axial hydrogens at C3 carbon atoms are called 1,3 diaxial interactions, which are not very well pronounced. It is pronounced when you have another substituent at C3. So, this becomes largely destabilizing effects when you have disubstituted cyclohexane. So, in monosubstituent, the major destabilizing effect are the gauche interactions and the minor ones are 1,3 diaxial interactions. And hence, the equatorial conformation becomes more stable because these interactions are absent in the equatorial position. The equatorial conformation is favored in the equilibrium because axial isomer has about 1.8 kilocalories per mole of steric strain, and this observation can be generalized to all the substituent and not only on the methyl group. If they are present at equatorial position, will always be more stable than the axial position. So, now we know that in monosubstituted cyclohexane, the substituent would be preferred if it present in equatorial position. Let us now study the disubstituted cyclohexane, and we will take the case of 1,2 disubstitution. Because of the restricted rotation around ring carbons, 1,2 dimethyl cyclohexane can exist as geometrical isomers, that is either cis or trans isomer. We have just discussed that a cis condition would be when you have one substituent at the axial position and the other one at the equatorial position, because they are both pointing upwards. This will create cis isomer, and if one is present at axial and the carbon atom 2 substituent is also present at axial, this will create a trans situation. Recall this: cis and trans isomers, they are geometrical isomers or diastereomers and cannot be readily interconverted by simple rotational process. A bond has to be broken to interconvert. They are not different conformations of the same isomer. As discussed, the cis isomer is the one where one of the methyl substituent occupies the axial position and the other occupies the equatorial position. We call it in short AE conformer, that means axial equatorial conformer, both the bonds pointing upwards, or vice versa. EA, that is both the bonds pointing downwards, as shown in the figure. AE conformer and EA conformer. Similarly, the trans isomer will have either both the methyl substituent on axial positions, that is AA conformer, that is axial up and axial down, or both on equatorial positions, that is EE conformer, equatorial up and equatorial down, as shown in the figure, EE and AA isomers. Out of cis and trans configurations, trans isomer would be more stable in its EE conformer, as both the methyls are placed at less hindered equatorial positions. Now, recollect the monosubstituted cyclohexane, where we established that substituent if present at equatorial position would be less hindered, and when you have two substituent, obviously both, if they are present at equatorial position, they will have the minimum steric repulsions. So, out of the 4 configurations possible, 2 of cis and 2 of trans, the trans isomer in EE rather than AA would be the most stable, since both the methyls are placed at less hindered equatorial positions. However, there is slight destabilizing gauche interaction between the 2 methyl groups in this conformation, amounting to 0.9 kilocalories per mole of energy. On the other hand, the AA conformation is highly unstable due to strong gauche and 1,3 diaxial interactions, raising the energy to 3.6 kilocalories per mole, 1.8 kilocalories per mole for each axial substituent. The cis conformers AE and EA are both equal in energy, and that is 1.8 kilocalories per mole, equivalent to 1 axial substituent, and can interconvert through ring flipping. The Newman projections of the chair conformations of cis and trans 1,2-dimethyl cyclohexane are shown in the figure, and we can see all kinds of interactions in this, whether it is gauche interaction or 1,3-diaxial interactions, and we can very well see that they are anti to each other because one CH3 is pointing upwards and the other one is pointing downwards in trans configurations, and in cis configuration both the CH3 are pointing. Now, let us take the case of 1,3-di substitution. That means, the two methyl groups are present on one carbon atom 1 and then carbon atom number 3. In 1,3-di substituted cyclohexane, the two geometrical isomers cis and trans are shown in the figure by using Newman projection formula. The cis isomer has either both the methyls on the axial position. Now, because this is 1 and 3, so axial and axial will become cis, whereas axial and equatorial will become trans. So, in this case, this cis isomer has shown having both the methyl groups either on the axial position, that is AA isomer, or both on the equatorial position, that is EE isomer. In the trans isomer, the one of the methyl groups are on axial and the other on the equatorial position in both the conformers, whether it is AE or EA conformer. The diaxial AA and diequatorial EE conformers of cis isomer has a considerable energy difference, and you can imagine that which one will be lesser in energy. Of course, it is diequatorial EE conformer where the interactions or steric interactions are minimum. The diaxial conformer is much less stable, not only due to the destabilizing gauche interactions, but due to severe 1,3 diaxial interactions. As I just told you, the diaxial interactions are very well pronounced when there are two bulky groups. Earlier it was only CH3 and H interaction at 1,3 diaxial positions, but now it is CH3 and CH3 diaxial interactions as shown in the following figure. As both the methyl groups lie on the same side of the ring and at 1,3 positions, they suffer strong strain due to axial methyl axial interactions, which are known as 1,3 diaxial interaction, as compared to axial methyl axial hydrogen interaction in monosubstituted monocyclohexane, methyl cyclohexane. These destabilizing interactions, that is gauche and 1,3 diaxial, raises the energy of diaxial cis isomer, resulting in a very insignificant amount of ring flipping, giving rise to this isomer. So, the possibility of this conformer to exist is very small. On the contrary, the diequatorial conformer is absolutely strain free, and thus the ring prefers to remain in this conformation, which is shown in the following figure. The trans isomer has both the conformers equivalent in energy, whether it is AE or EA, and thus the ring flipping occurs without any preference. As shown in the following figure, the ring is flipping and the energies of both the conformers are absolutely equivalent. Out of the cis and trans isomers of 1,3 dimethyl cyclohexane, the cis isomer is the most stable, where both the substituents occupy equatorial positions. Note that both the conformers of trans isomer are less stable than the diequatorial cis isomer, mainly due to the gauche interactions, but are more stable than the diaxial cis isomer, because in diaxial cis isomer you have severe 1,3 diaxial interactions which are highly destabilizing. Now, consider the case of 1,4-di substitution. The cis and trans isomers of 1,4-methyl cyclohexane are shown in the following figure. Again, you have the case of cis and trans absolutely equivalent to the monosubstituted one. That means axial and equatorial will be cis and axial would be trans. Note that in the cis isomer, one of the methyl groups occupies an axial position while the other occupies equatorial position, that is AE conformer. The ring flip reverses this arrangement and we get EA conformer having identical amount of strain. Hence, the two conformers AE and EA are equal in energies and are easily interconvertible. On the contrary, the trans isomers differ significantly in energies between AA and EE conformers. The di-equatorial EE conformer has no strain at all, as both the methyl groups lie on the less hindered equatorial positions. The ring flip gives diaxial conformer, which has considerable strain due to gauge interactions between the methyl groups and the ring methylene. Each axial methyl group faces two such gauge interactions with the ring methylene and caused 1.8 kilocalories per mole of strain. So, the diaxial conformer has 4 touch destabilizing interactions and thus has 3.6 kilocalories per mole, that is 2 into 1.8 kilocalories per mole of strain for each methyl group. Now, let us summarize actually which conformers of all disubstituted cyclohexanes are more stable. The table shows the position of the substituent as 1, 2, 1, 3 and 1, 4, and you can identify the most stable isomer in each case. In case of 1, 2 disubstituted cyclohexane, the most stable configuration or conformation is trans, that is EE. In 1, 3 disubstituted cyclohexane, the most stable conformation is cis EE, and in 1, 4 disubstituted cyclohexane, the most substituted conformation is trans, that is EE. It can be concluded from the table that placing the substituent on the equatorial position always leads to stabilization. Both trans 1,4 dimethyl cyclohexane and cis 1,3 dimethyl cyclohexane have essentially the same energy, since neither of them has any strain at all. Let us summarize now what we have learned in this module. We have learned that stereochemistry is the study of 3D structures and shapes of the organic molecules. It allows us to visualize, draw and understand these molecules in a better way, and also to analyze and predict their behavior in three-dimensional shape. The different shapes that a molecule can assume due to rotation around single bonds are called conformations. And the study of molecular conformations and their relative energies is called conformational analysis. The stabilities of cycloalkanes can be compared by using their heats of combustion data. Minimum values of heat of combustion suggest maximum stability. A puckered structure of cyclohexane has 0 angle strain, which is completely in contrast to the Baeyer strain theory. And various types of strain that we need to be familiar with while working with cycloalkanes are angle strain, torsional strain and van der Waals strain. Cyclopropane is considerably strained molecule with all the atoms in a plane and all CH bonds completely eclipsed with no possibility of rotation around carbon-carbon single bonds. Cyclobutane on the other hand adopts a puckered or a wing shaped conformation to relieve the torsional strain, but in doing so acquires a little angle strain. So, there has to be always a balance between the angle strain and the torsional strain, and the most acceptable conformation would be where the energy is maximum, where the two opposing strains are actually becomes minimum. The cyclopentane adopts either an open envelope or a twist conformation and keep changing the envelope flap around the ring, generating 5 possible puckered conformations, and thus have less well defined conformational properties than the rest of the cycloalkanes. Cyclohexane in chair conformation is strain free, as all the CH bonds are anti to each other and there is no angle strain. It can have 2 chair conformations, the chair and the inverted chair. This can be interconverted by ring flipping. Ring flipping changes all the equatorial bonds to the axial bonds and all the axial bonds to the equatorial bonds. Other significant conformations of cyclohexane are boat conformation, twist boat conformation and half chair conformations. And the relative energies of these conformations are chair being the most stable, then twist boat, then boat, and most unstable is the half chair conformation. The boat conformation possesses torsional strain due to eclipsing of the 4 CH bonds and also the flagpole interactions. It is 6.9 kilocalories per mole more in energy than the chair conformation. Twist boat and half chair conformation are more in energy than the chair conformations by 5.5 kilocalories per mole and 10 kilocalories per mole respectively. Monosubstitution in cyclohexane prefers equatorial position, which is free from gauche or steric strain as compared to the axial position, which is energetically destabilized due to gauche and 1,3 diaxial interactions. One axial substitution roughly costs 1.8 kilocalories per mole of energy. Same is true for disubstituted cyclohexanes, where the preferred position of the substituents are always equatorial over the axial.